Welcome to the Explainer. So, let me ask you something. Have you ever wondered if true and false are really the only two options we've got? Today, we're going to leave the familiar shores of everyday logic and journey into the wild, fascinating, and sometimes strange landscapes of non-classical logic, worlds where the very rules of reason get a complete makeover. Centuries, classical logic has been our rock. It gives us a solid yes or no, a true or false for pretty much any question. And you know what? It's clean, it's incredibly powerful. But what happens when reality is, well, a lot messier than that? What do you do when you need to talk about what's merely possible or what's absolutely necessary? Or what happens when the information you have is incomplete? Here's a cool way to think about it. If classical logic is like the perfect, predictable grid of the geometry you learned in high school, Euclidean geometry, then non-classical logics are like the totally mind-bending worlds of non-Euclidean geometry, where parallel lines can actually meet and the fundamental rules just change. We're not just finding new places on the old map here, we are literally discovering entirely new kinds of maps. Now, to navigate these strange new logical spaces, our old tools just aren't going to cut it. We need a completely new kit, and that kit is called proof theory. It's what gives us the specialized compasses, the coordinate systems, and the maps we need to actually chart these territories and make sense of their unique structures.
Okay, so our first expedition is going to take us into the realm of modal logic. This is the logic of possibility and necessity. So, to really understand statements like, it might rain tomorrow, or this must be true, modal logic imagines this vast network of interconnected, possible worlds.
So you might be wondering, how do logicians even begin to chart these worlds? Well, they use a framework called Kripke semantics. Think of it as the master map. It defines not just our current world, but all the other possible ones, plus the rules for how we can access or kind of travel between them. A statement could be true right here, but totally false in an alternate world we can get to from ours. So, if Kripke semantics is the map, how do we track an argument as it zips through all these different worlds? This is where a really brilliant tool comes in, called labeled sequent calculi, or LSC for short. This is like giving every single step of your proof a GPS tag. Each statement gets labeled with the world it belongs to, which lets us build super precise arguments that respect the unique geography of all these possible worlds. And, LSC is just one tool in this massive navigational toolkit. Depending on the terrain, the specific logical system you're exploring, you might need a totally different kind of map. You've got hypersequence, nested sequence, display calculi. Each one is a specialized system designed to chart a different, totally unique logical universe. All right, our expedition continues. We're leaving that multiverse of possible worlds behind us, and now we're entering a universe with a completely different twist. This is a universe where reasoning actually has a cost, and ideas themselves are treated like finite resources. This is the really radical question that's at the heart of what we call substructural logics, and the most famous one is linear logic. It forces us to be incredibly disciplined by changing rules we normally just take for granted. It makes us treat our premises not as these abstract truths, but as tangible items that can actually be used up. Think about it like this. In classical logic, if you know A is true, you can use A to prove a dozen different things, right? You can copy it, reuse it infinitely, no problem. But in linear logic, if you use premise A to prove something, poof, it's gone, it's consumed. This creates a kind of resource-aware reasoning that has some really profound implications. Okay, so visualizing this flow of resources can get super messy with traditional proofs. So logicians developed this absolutely incredible tool called proof nets. The best way to think of it is like a subway map. It strips away all the confusing syntax and just shows you the direct connections, the most efficient path from your starting resources to your final conclusion. It's a purely graphical way to see the journey that a proof takes. So we've seen these intricate maps for possible worlds, we've seen these complex resource management systems, but what's the ultimate goal here? What are these logical explorers really searching for on these strange and complex journeys? The ultimate prize really is elegance and clarity, and it's achieved through a process called cut elimination. Now, a cut is basically a detour in your proof, a lemma, a roundabout step. Cut elimination is the art of removing every single one of those detours until you're left with the most direct, beautiful, and essential argument possible. It's all about finding that perfect, elegant path. And this whole quest for elegance isn't just about making things look pretty. It gets out a much deeper philosophical truth, one that's captured by something called proof-theoretic semantics. The big idea is that the true meaning of a logical concept like and, or if-then, it isn't some abstract definition somewhere. Its meaning is found in how it's actually used inside these elegant, direct proofs.
But here it is. Here's the most stunning discovery of all. The real secret treasure at the end of this whole exploration. Through this deep, beautiful connection known as the Curry-Howard isomorphism, it turns out these elegant proofs aren't just arguments. They are, in fact, computer programs.
Yeah, you heard that right. A formal proof is literally the blueprint for an algorithm. And that process we were just talking about, cut elimination, finding the most elegant path, that is literally the same thing as executing the program. This forges this incredible link between the abstract world of pure logic and the very concrete foundations of computer science. And that leaves us with one final, truly mind-bending question to chew on. If designing a new logical system with new rules is the same thing as designing a new model of computation, what kind of new programs are we making possible? By exploring these strange new logical worlds, what new computational realities are we getting ready to bring into existence?